Okay, so we're recording. Okay, so you've looked at this before when you were finding the limit as x approaches a of f of x minus f of a over x minus a. So this here, we're talking about taking a point A. So you can see if I scroll this up a little bit. Here's the point A, okay? And then any other point on this curve defines a line. So between this point and this point at x equals a, we've got a secant line, right? But if we let x, this value, get closer and closer and closer to a, then the slope of this line becomes the slope of the tangent. Okay? And that's what you were talking about with Mr. Runke, like almost 2 weeks ago, probably today. Okay? Do you recall doing that? Okay? So that's what we're talking about. Now, what that does, when we take that limit, is it gives me the slope at A. What we want to define today is the slope at any position on this graph. Okay, so for any x value, not just at x equals A. And that's where it gets a little bit trickier, but it's not too bad. Okay? And you'll be able to follow it. So if we take the limit as x approaches a of f of x, we get the slope of the curve at x equals a, or if you want to define it as the point here, the point a comma f of a. So it's x and y. Those are the x and the y values. So the x value is a, and the y value is the value of the function at a, if the limit exists. Okay? If the limit doesn't exist, then the slope's undefined. The limit, we say, does not exist for whatever reason, and we'll talk about why the limit might not exist at those points, but I'm sure you could think of some reasons why. Okay? Don't show this message again. Let's do that. Okay, any questions for me so far? It's just kind of a review of things that you've already looked at. Okay? Okay. Now, what if we don't want to know just the slope at x equals a, but we want to find, let's back it up. One of the things that was showing up on your assessment from not last Friday, but the Friday before, is that you were either not reading the question properly or you didn't know what to do. But once we find the slope at x equals a, then we can find the equation of the line that is the tangent line at this point, okay? So we will need the slope and the point to find that line, and you know how to do that, I'm pretty sure, but in most cases, people forgot to find that, even though that was part of the question. So I'm not sure why that is, but we'll do some more practice with that today, okay? So here's an example. So let's say we have a function that's defined by 4t squared plus t. At the point 1, 5, we are wanting to know what is the equation of the tangent at this point. Okay? So this is similar to the question that you were asked in your assessments for this learning outcome. Only the assessment specifically said, find the slope of the curve at x equals 1, and then write the equation of the tangent line. Okay? And so what most of you tried to do is find the slope at x equals 1, and some of you were successful and some of you weren't. And then only about 2 or 3 of you actually went on to find this equation of the tangent at this point. I should say probably 4 or 5 of you went on to find the equation of the tangent at this point, or tried to. Okay? So you're going to see this come up again on your assessment this Friday, so it's good for us to practice it. And it will be actually linked to the definition of the derivative. So we'll be looking at assessing 2 learning outcomes in one with these kinds of questions. Okay? So you'll get to reassess for the learning outcome C, I can't remember which one it was. I want to say C6 or C7. And then you will also get credit for this learning outcome, which is D1. Okay? Slope of the derivative. Okay, so first thing we're going to do, we're going to use the limit function. Okay, so we're going to take the limit as x approaches a of f of x minus f of a over x minus a. So the limit as x approaches 1 of f of x minus f of a all over x minus, oops, we make the a equal to 1. Okay? No, it's 1 comma 5. That's the point. Yeah, thanks. What's a comma? Okay, so we are going to substitute in f of x. Actually, we're talking about t today, aren't we? So these should all be t's. So we have 4t squared plus t, and then we're subtracting the value of the function at 1, which is 5, all over t minus 1. Okay, are we all right with that? Now, this factors, hopefully, and we need it to factor in order to cancel out this t minus 1, because otherwise we're going to have 0 in the denominator. So we want to try to factor that. We're looking for two numbers that add to 1 and multiply to negative 20. So we're talking about add to 1, multiply to negative 20, so that's 5 and negative 4. So if we want to make 5 and negative 4, that means I want to have minus 1 there, and I want to have a plus 5 there. Okay? Everybody agree with me that 4t squared plus t minus 5 factors to be 4t plus 5t minus 1? Mm-hmm. Okay? So if that's an area that you need to, of concern, you're going to need to do a little practice with your factoring skills, but we can check it. 4t times t is 4t squared. Then I have minus 4t plus 5t, that gives me the t, and then 5 times minus 1 is minus 5. Okay? So that's nice, because clearly the t minus 1s here will cancel. And so I get the limit as t approaches 1 of 4t plus 5, which is 9. Okay? Everybody okay with that? So what does that number represent? The slope. So this is the slope at that point. Okay? That's what we just found. The slope of that curve at the point 1 comma 5. So we're halfway to answering this question, because the question didn't ask me to find slope, although I did need to find slope to answer the question. What did the question ask me to find? What about the tangent? The equation of the tangent line. So now all I've done is I found the slope of the tangent line. Now I know the point and the slope. And you can use slope point form, which many of you did try to do. So slope point form says we would go y minus 5 equals 9x minus 1. Slope point form is we take y minus the y value of the point, and then the slope and x minus the x value of the point. So y minus y1 equals mx minus x1. Okay? Is slope point form. But more traditionally, and certainly next year, I don't think you're going to see people using slope point form. You're going to see people using slope intercept form. Okay? Slope intercept form takes a little bit more work to come up with, but it's really not bad at all. The slope is 9. The point is 1, 5, so you plug that in for x and that in for y and figure out what b is. Okay? So I would have 5 equals 9 times 1 plus b. So 5 minus 9 is minus 4, so b is minus 4. So I'd have y equals 9x minus 4. Okay? Which is in fact also what you would get if you expanded these brackets here and solved for y. You get y equals 9x minus 4. So you could try that here. Y minus 5 equals 9x minus 9. Y equals 9x minus 4. When I add the 5 over there. Okay? Hi. Questions on a sleepy Monday morning? about that? Okay. When we come back from spring break, we come back on a Tuesday, so I don't know why. My brain was on the mode where my first day of work was going to be a Tuesday, so I thought it was Tuesday today when I arrived. I don't know why that is, but it's not. It's Monday. Okay. So on the assessment from a week ago Friday, if you had done it like that, you would have ended up with the correct answer, okay? And certainly the first one was more straightforward because it was simply a polynomial, like this is, a polynomial function. But the second one was more difficult because it has the rational function. So you had to use a little bit more algebra in order to simplify it at the limit stage so that you got something that you could actually find the limit of, okay? So some people, that's where we fell apart in that second assessment. What we have to be able to do today, however, is to use method 2. So if you recall when you were learning how to do slopes of tangents, we learned method 1 and method 2. And method 1 was easier than method 2 for the most part, for most equations. But we have to learn how to do it with method 2. And the reason is because we want to find the slope of the curve at any point x, not just at a certain value of x, but at any point x. So that means that we're going to use method 2, and method 2 looks like this. So this is the actual definition of the derivative that we're going to use. The derivative at x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. This is a little bit messy, so I'm going to fix it up a little bit. Still looks not good. Okay, so notice in this definition we have no discussion about what A is. We're not approaching a particular point. We're going to leave it in a very general form with, we'll still have x's. So the limit will end up being another function. And that is in fact the derivative because it will be the derivative of f of x at any x value. And so we'll be able to find the slope at any x value, so we can do it over and over and over again because we'll have this general function. And that's our goal, okay? Is to be able to use that particular limit equation, okay? So it's the same idea if this is x here. Now we're going to go h away from x, so we'll end up here, and that's x plus h. So we have that secant line, okay? But we're going to let h get closer and closer to 0, so now we're getting closer and closer and closer and bringing it back to this point, and we're getting the tangent at this point. But this point isn't defined by any particular value of a, it's a point at x. Okay? And that's why it's valuable to us, is because it's allowing us to figure out the slope at any point. So we're going to find a general equation for the slope, and then we can find the slope at multiple points if we want to. Okay? So we'll do some examples using method 2 today, and that's what you'll be practicing, is how to use method 2 to find the derivative, to find the slope of the tangent in a general form. Okay? And so we'll start with an easy one. But any questions about this? Okay. All right, so we'll start with an easy one. Find the derivative of 3x squared. Okay. So we're going to use the equation of the limit, which I have on the board here for you. Okay. So we want to find the derivative with respect to x. So it's the limit as h approaches 0, okay, of f of x plus h minus f of x all over h. Okay, and this is the part, well, in this particular equation it's not that difficult. So what we want to do is we want to replace x in this function with x plus h. So we have, instead of x, we have x plus h squared. Okay? So with this particular setup, the beginning is difficult, but then when it comes time to divide through by the h, that part's the easy part. So the factoring situation is less cumbersome, but it's the simplifying the numerator part that you will find tricky. Not necessarily in this case, but in some of the more difficult cases. Okay? But notice that it's 3x squared. So for this one, I'm substituting x plus h in for the x. So it's 3x plus h squared minus 3x squared. Okay? So now we're just going to get rid of brackets and simplify everything. So we have x squared plus 2xh plus h squared so we have 3x squared plus 2x 6xh plus 3h squared minus 3x squared all over h. Now I have 3x squared, take away 3x squared, so I'm just left with 6xh plus 3h squared all over h, okay? Which is beautiful because now you can see what? Now we can divide h into every term. So I have 6x plus 3h. But when we let h go to 0, that term is going to be gone, and I'm just ending up with 6x. Okay? Okay? Does that make sense? So what that tells me is that the slope of the tangent at any value of x is 6 times that value of x. So if we knew that x was equal to 2, the slope would be 12. And if we knew the slope at x was 5, the slope would be 30. And if x was negative a half, the slope would be negative 3. Okay, so that allows me to find the slope at multiple points on the curve rather than just finding the slope at a single point on the curve. Okay, and that's the derivative. 6x is the derivative of 3x squared. Okay? So then I could say, okay, now I want you to find the equation of the tangent at the point, you know, where x equals 2. And so you'd say, oh, well, the slope's 12, and when x equals 2, y equals 12. So I have the point 12, 12, and then I'd find the slope, the equation of the tangent at that point. Okay? All right, so let's do it for this one. Find the derivative of f of x when f of x equals x cubed. Okay. So we want the limit as h approaches 0 of that. X plus h cubed minus x cubed over h. Okay? So now you've got to expand x plus h cubed. So go ahead. Do the expansion. Subtract x cubed. Divide through by h. And take the limit as h goes to 0. What do you get here? So we're missing Austin today. Renee, I knew about. And who else is normally at your table? Jack, right. So expanding that x plus h cubed is a little tricky. Right, yeah. You can memorize expanding a cubic. Or, of course, you can just square x plus h squared, which we did up above, and then multiply that through by x plus h.
What are you talking about? Of course you did all the work. I didn't do anything.
So put up your hand when you have the derivative and I'll tell you if it is correct. Uh-huh. Yeah, where's the work for it?
I'm working on the work.
Good, yeah. Yeah, good. Getting there? Okay. You got it?
Yeah.
Good. You getting there? You should have. Oh, you did that one. I see what you're saying. Yeah, yeah, right. Uh-huh. That's right.
I can't run on this.
Can you expand x plus h cubed? You can do it, Kenny. I know you can. This should be 2xh.
There's still an expectation.
Yeah, but when this expands, you get 2xh there. So that does make a difference here. Did you get it? Oh, good, yeah. Okay?
I'm confused.
Okay, what's confusing?
Read your alphabet.
Well, you've got to subtract the x cubed, right?
Oh, yeah.
So that's just the cubic. Combine your, oh no, so subtract the x cubed, and then divide everything by h.
Yeah. We got 3x squared.
I'm going to say that, h approaches 0. Okay? So when you expand the cubic, you get x cubed plus 2xh squared plus, am I right here? I'm just guessing, 2x squared h. Is that right? No. No? What's wrong? I'm missing a negative in there somewhere, aren't I? No, I'm not. Oh, right. Yeah, because I'm going to end up with, right. 2 of one and 1 of the other. So I end up with 3 x squared h plus 3xh squared plus h cubed minus x cubed all over h. Okay? And so then I take the limit as h approaches 0. These are gone. I'm going to divide everything through by h, so I'll have 3xh plus, nope, this is wrong, plus 3x squared plus h squared. Okay? And then all the terms that are left with h go to 0, and I'm left with 3x squared. Okay? See how that works? All right, now I just want to show you, what does it look like when we graph this cubic? If we were going to graph f of x, what does that look like? What is f of x?
Up from the, it goes up, and then it goes down the other.
Okay, we get that S curve happening, right? What happens when we graph this? What does that look like? A quadratic is a nice parabola, right? Shaped like this. Kind of narrow. So what that's saying is that for all values of x here that are positive, we get a slope that's positive. So we get a positive slope. So this is the slope, right? So the slope is positive and increasing. And notice with the green graph, the slope is positive and increasing. And here on this side, all my y values are still positive. And here all my y values are still positive. So it's showing me how the slope is changing as the graph is changing. The slope is positive everywhere except I didn't do a very good job of drawing it. What happens to the slope right here for the green graph? The slope is 0. And what happens to the y value of the black graph right there? 0. So the slope is 0 because the black graph is the graph of the slope and the green graph is the graph we're talking about. Let's go back and look at this one for a moment in the same manner. So here I've got the green graph is 3x squared. That's a little too flat, so I'm going to try that again. So there's 3x squared. The derivative is 6x. So 6x looks kind of like this. Okay. Notice on this side, the black graph, the y values are all positive, which tells me that the slope everywhere there is positive. And so definitely do. We have a slope here that's positive everywhere. The slope right here is 0. Okay, and the black graph is the y value 0. Here the black graph has y values that are negative everywhere because the green graph has a slope that is negative everywhere. Okay, so the values for the black graph correspond to the slope of the green graph. Okay. Anyway, it's just something to think about because we can graph those as a function. Let's do one other one. What I got there. What if we had a function that was 3x squared minus 2x? How would we find the derivative of that? Okay. How would we find the derivative of that? I'm pretty sure that's similar to, if not exactly the same as, the function that we were finding the derivative of on your test paper, but we want you to use method 2. Okay. How am I going to do f of x plus h there? That's the thing to watch out for. F of x plus h.
Bracket x plus h, close bracket squared, minus 2 bracket x plus h, close bracket, over h. Get minus.
Okay? So we have to put x plus h everywhere there's an x in the original function for f of x plus h. Okay? And so that's something to remind you of with your function notation. So then, all right, what we need to do is, of course, Simplify the top. Divide through by h. And then take the limit. So I'm going to have 3x squared plus 6xh plus 3h squared minus 2x minus 2h minus 3x squared plus 2x. That's a 2x. All right, so the 3x squareds and minus 3x squared gone. The minus 2x and the plus 2x gone. And then we're going to divide through by h everywhere. So we get 6x plus 3h minus 2. And we let h go to 0, and we get 6x minus 2. Okay? Yep. Scrolling that way?
Yes, thank you.
Okay. But the point I want to make with this is that when you are taking the limit of f of x plus h minus f of x over h, you've got to put the x plus h in here, and then simplify that. Okay, so it looks messy, but it does simplify in the same manner. When we divide through by h, we end up with that. We let h go to 0, we get 6x minus 2. All right, now you're going to have to plug in. Okay. Okay, I went through that one a little bit quickly because I was worried about running out of power, but now I don't have to worry about running out of power. Questions about that? Emily, are you following it?
Yeah.
Yeah. Okay. Okay. So you are going to practice a lot of that in the next couple of days, today and tomorrow. But let's talk about differentiability, okay? Because not all functions are differentiable. In other words, we're not going to be able to do this in all cases, okay? Not all functions will have a derivative, and that's what it means to be differentiable, is to have a derivative, okay? Some of them will be differentiable in some places, but not other places. But by definition, oh, that's interesting, because I pushed everything down, so it came out of it. In order to be differentiable at a point where x equals a, f of a must exist, and f prime of a, so in other words, the derivative must exist at a. And by that we mean the two-sided limit. So we need to be able to take the limit on either side of x equals a and have the value be the same to say that the two-sided limit exists, okay? So that the limit exists. So the function has to exist and the limit exists, and that way we have differentiability. Now, these are the kinds of functions that might not be differentiable. This situation, this absolute value situation, we do not have differentiability right here. This is called a corner. And at this point, the limit on this side is different from the limit on this side. Why? Why are those limits different? What are we finding when we're finding the limit? We're finding the limit that tells us the derivative. The derivative is the, starts with an S, slope. And notice the slope on this side is different from the slope on this side, and it doesn't change gradually like in a parabola, okay? It changes immediately at that corner. So this function is not differentiable at x equals 0. It has a corner there, okay? It's continuous though, isn't it? This is a continuous function everywhere. There's no holes or gaps or tangents of any kind. but it's not differentiable at the corner. Okay, because the slopes are different on either end and they don't gradually change, or on either side. Okay, so this is an absolute value function. So absolute value functions are not differentiable everywhere. They're differentiable all the way along here and all the way along here, but just not at x equals a. Okay, which in this case is 0. Questions about that? Okay. So another situation where we might have differentiability, or we might lack differentiability, is a cusp. Okay, you've not heard them necessarily called this before. I want to scroll it up a tiny bit. Okay. I have to do that. Sorry, I have to cut off that first line. Okay. So f of x equals x to the power of 2/3. If you wanted to put this into your graphing calculator, this is how it would graph. Okay. So again, notice that the function has a slope on the one side that's positive and a slope on the other side that's negative, and that change is dramatic right at this point, okay, which is called the cusp. Okay? And in fact, the slope is positive, but it's approaching positive infinity as we go towards x equals 0 from the right. And as we go towards x equals 0 from the left, the slope is approaching negative infinity. Okay? So the slopes on either side of that point are not the same. And so therefore we have a lack of differentiability. That we cannot take the derivative at x equals 0 in this case. Okay? The function exists because you can have 0 to the power of 2/3. What is 0 to the power of 2/3? 0. So that point exists, the function exists there, but the slope doesn't exist there. And the slope doesn't exist here. Okay? So we don't have differentiability. So we can have continuity and not have differentiability. Okay? If we don't have, well, and of course another situation would be this case. So here we have continuity, but, so this is the function f of x equals x to the power of 1/3. What we have right here,
Make you scroll up to the end.
yeah. When we have a vertical tangent, what's the slope of a vertical line?
Undefined.
It's undefined, right? It's infinite slope. Okay? So because in this case, the tangent line at x equals 0 would be vertical, okay? Then it doesn't have a slope there. It's not zero slope. Zero slope is a flat line, but a vertical line has an undefined slope. And so it's not differentiable here at x equals 0. Okay? So those are all three cases where we have continuity of a function, but we don't have differentiability. And obviously where we have discontinuity, holes, vertical asymptotes, gaps, okay? So any discontinuity, we're not going to be able to differentiate at A here either, because the function doesn't exist. So the function has to exist, that's part A. And so for continuous functions, they exist everywhere, but also the slope has to exist. Okay? So if this doesn't exist, then we know we're not differentiable. But if this exists, we now have to look at what's going on with the slope everywhere. Whether the slope exists everywhere. Okay? So if f is differentiable at A, then it is continuous at A, but a function can be continuous at A and not be differentiable. Okay? So differentiability everywhere implies continuity, but continuity doesn't guarantee differentiability. Do you understand the difference? Right? If we can find the slope of the line everywhere, then the graph must be continuous everywhere. But if the graph is continuous, that doesn't mean that we can find the slope everywhere. We saw those three examples: corners, cusps, and vertical tangents. We're not going to be able to find the slope everywhere, even though the function is continuous. Questions for me about that? Kenny, put your phone away, please. Thank you. Okay? Is it making sense? You'll have to put some of this into practice. The only other thing I wanted to show you today is just notation. So we've been using this notation for derivatives, but you will also see this. Pardon me? Yeah. Sorry. Okay? So remember, f of x is just one way of stating a function. So when we put the little prime in there, that means take the derivative. It's an apostrophe, so f apostrophe of x, that we say f prime of x. We can also see y prime. So y prime also says take the derivative of y. But there are other notations, so I want to show you some other notations. We're going to talk about taking second and third derivatives, although they're not as fun to do. No, we're not. I'm just going to do notation with you today. We'll just worry about second and third notations another day. Okay. We're doing all right, Alex? Can I?
Yep, you just go.
Okay. So this is a pretty standard notation as well. dy by dx. And that's, if we were to read that out, it says take the derivative of y with respect to x. Okay? dy by dx. Now, d here, it looks like a d, but really it's a delta. But it's a small letter delta. So we've seen the big letter delta before. What does the big letter delta look like? It's a triangle. So you've seen this before. What did we use this before? Slope, right? Delta y over delta x is slope. Now when we use the dy by dx, we are using the small letter delta, and all we're saying there is we want the slope of the tangent because we want to let the dx go to 0. So the delta x is going to approach 0. We're taking the limit as x approaches 0. And so it's exactly the same notation, but we're using the little letters to remind you that we're going to have a little interval. In fact, an interval that is non-existent, right? We're going to let it go to 0. Okay? And then here's a more cumbersome notation. Here's take the derivative of f of x with respect to x at x equals 4. Okay? So it's a little more cumbersome, but it's a notation that allows you to say all of that without having to write it out. Take the derivative of f of x with respect to x at x equals 4. Yeah?
Is the x equals 4, that's just an example? Or is that
Right, so that would be finding the slope at x equals 4.
okay?
Right? And here it would be finding the slope at any x value.
Cool.
Yeah. Okay? Okay, so I'm going to turn you loose today and tomorrow to practice from your... Yeah, we're going to keep working on it tomorrow. So we're not going to do new material tomorrow. We're going to keep practicing using the definition of the derivative to find the equation of the derivative at any value x. Okay? So if you are working out of... If you're working at a third edition, we're talking about pages 88 to 99. Okay? So third edition, 88 to 99. And have you guys got second edition? No. Second edition? Can I have a look, Leo? For you guys, it's 72 to 80. So clearly edition has some more practice than the second edition, but I will provide some more
So,
practice tomorrow.
grade 72 to 80 for second edition.
Yes. Yeah.